Welcome to another live stream on the assumptions of physics. Today we are going to go back to an old open problem because there have been some people in the community that have been discussing and making some progress. So we are going to review what has been done and what hasn't been done. Maybe I'll pull out a document to see what is it that we're going to talk about. I'm slightly not ready, but let me go get it. Hopefully, if I just look on the open problem section, there is going to be a link on the things that I want to show. That is, if my internet works. And of course, we are live, so it's not gonna work. And this is why I have to prepare everything before. No, nothing. This is absolutely not working. Okay. Okay, let me share this. Okay, so what we need to talk about is there a link here? Yes, there we go. So we saw that in classical mechanics, if we decide to formulate the symplectic form in terms of position and velocity, we get this form where the mass times the metric tensor appears on the position velocity part of the symplectic form, and in the position part appears the electromagnetic force tensor, and appears this G alpha beta gamma contracted with the velocity. And this G alpha beta gamma is basically some type of curl on the first index on G. And so this raises the question, because this is not something that appears typically when people do differential geometry. And so the questions are, since this appears where the electromagnetic force appears, can I interpret this whole thing as some type of inertial force or not? Since we know that the metric tensor represents, the symplectic form is something that allows us to define the entropy on phase space, what do both of these terms mean in terms of that? How do the G alpha beta gamma influence the appearance of the entropy? What happens in the entropy is effectively in non-Cartesian coordinate system. That's probably what's going to happen. And in another question is for example, what happens when these are zero? And what happens, I don't know if I had it here, but one of the things that happens if all these terms are zero, probably it's there in the open problem, these basically you can write the metric tensor as the Hessian of a scalar function, and this kind of looks like what you have with Kähler manifold in quantum mechanics, where you have a metric that is generated by some type of Hessian, even though it's complex, and so it's a little bit different. And so the question is, can we make sense of this pseudotensor, understand what it is, and characterize it, because since it appears so naturally, the instinct should be it should be important. So Logan has prepared a set of slides for what he has found and other people has found. So I'll give it up to Logan, and please go ahead.
All right, I'll come here and share my screen. Hopefully this all works like it was before. All right, is it all shared and everything? Is it working for you?
Yes,
Okay,
it's
perfect.
streaming correctly.
Okay. Okay, so just for conventions, I'll use the factor out in front of the symmetric and anti-symmetric parts, so that every tensor will decompose equally into the symmetric and anti-symmetric parts, and that changes the wedge product. This is I make note of this because this differs from the conventions used in the assumptions of physics document, where the wedge product is just directly the difference without the factor of 1/2.
Okay.
So the way I started was sort of more from the mathematical side, and then reconnecting with the physics, and tried to make everything as formal as possible. And the way I did that was defining metric one forms, where for each value of sigma, h sub sigma is just a one form on the manifold, and you can evaluate the exterior derivative of that. And because it will be anti-symmetric, the term you get is their equation 2, and this object G appears, and the definition is given there in equation 3. I also note the relationship to the anti-symmetric Christoffel symbols, which becomes important with some of Julius's work and Isaac's work with frame transport, and how G can appear effectively whenever the Christoffel symbols appear. This object should correspond to something happening physically. And then this is just a note of why these metric one forms are natural objects to study in the first place, besides just a random mathematical thing we would define. And that's because the sigma metric one form will extract from a vector field its sigma covariant component. And if we sum all of these together, or I shouldn't say sum all of these together, if we combine all of these together, we get the covector field associated with the vector field.
Yeah, let me digest it, because the
Yeah,
whole
yeah.
that notation is really like something that. All right,
Yeah,
so
that's because I was using a mix of both index and index-free notation, because for me the index-free notation is more natural, but I also know that in physics the standard is to use the component notation.
Yeah, also because there is the whole issue that the symbol mean different things. So even if you're in component notation but you write dx, that dx
Right.
is still a
Still,
one form for you.
yes.
And for me, it's instead the dx is typically something else. So and I'm
Right.
trying to digest what is it that is going on. So
Yeah.
basically, that's
So
just
this is
contrasting.
just right for a fixed sigma index. So in the same way for a tetrad, when we have Latin components, we just the Latin index we generally treat as fixed. So this is just for each fixed sigma applying to the vector field itself, not necessarily just applied to the vector components, but applied to the entire vector field will yield one component.
Yeah, so basically the H sigma is just picking out the component of the vector.
Yes,
That's
it's picking out
essentially
the
what's done.
covariant component of the vector.
And
Yeah,
then it says the sigma component, it's
is
it.
it? Yeah, it's the of the yeah the so you start with the vector field x, and if you lower the vector field down to the cotangent bundle using the metric, where once again I'm using the index-free notation using the flat symbol.
And so
Um,
what doesn't? Okay, so I'm trying to understand what this is. No, so the x lower sigma is a one form that takes.
it no it yeah a h lower sigma is a map from the cotangent. Sorry, a map from the tangent bundle to individual cotangent. Well, yeah, yeah.
This is exactly
Right.
why
No,
I
no.
hate this
See,
notation. It's
right. Yes.
completely confusing to me. Okay,
Um,
so X is a vector field, okay, and
yes.
H
And when
sigma
you
is getting
apply
a
when you
but
apply
it's
h sub sigma, you just get a function. You get a function. X sub sigma is one of the components of the covector field, which is just a function over the manifold.
right, but then
Because h sub sigma is a one form in and of itself, so we apply it to a vector field and you'll get a function. Now,
right.
we these functions that we get for each value of sigma naturally assemble together into a covector field.
Right, so the thing that's absolutely not clear to me is that if I got the component, I would get an X upper sigma, not an X lower sigma. So I don't understand why, if that's a scalar function, why do I get the the lower form?
Because we have part of the definition of the metric one form, we have the metric in there, which will lower it down to the cotangent bundle.
Okay, okay,
So
now I see what's
there in
going
the
on.
in the middle of equation 4, the dx
Yes,
mu
okay.
and partial nu will turn into a delta, change the new index to a mu, and then the
Yes,
metric will lower it
okay.
down to sigma.
Right, because the real thing is that I'm contracting x nu with g nu
Yes.
sigma. Okay, that's what
Yeah.
we're doing. So I'm getting the component and I'm okay, and I'm doing the inverse in terms of units, and
Mm-hmm.
then the sigma, the component of x. Okay, so what is x flat now? It's
It's
a one
the
form,
or covector field over covector field, which is a one form.
right? Which is gonna get is basically going to do the inner product between the incoming vector field and the
Mm-hmm.
vector field of x. Okay.
Mm-hmm. This is a lot of math, just like formalism that's not particularly that important. But I wanted to include it as a way of staying very mathematically rigorous and grounded. Um, this is basically just what was done with, for example, when in your introduction on capital G, you wrote that if all of the capital G components vanish, the metric must be generated by some Hessian potential.
Yeah.
This is basically just making the applications of Poincaré's lemma rigorous, but instead of considering the case of all components G mu nu sigma vanishing, this is asking what does it mean for a particular combination of G mu nu sigma indices to vanish. And it's not particularly that important as far as the mathematics go. I'm trying to find here. Right. So what I defined here with U restricted to mu nu is basically it's coordinate dependent. It's the mu nu coordinate sheet that is over a point x naught. And what it means for a particular combination of mu nu sigma indices on capital G to vanish means that the metric, the sigma sector of the metric, is generated potential on the mu nu plane.
Yes.
That's right. So it has to do basically with the sigma sector of the metric curling in the mu nu plane. And that gives us an understanding of each particular combination of indices rather than just the condition that all components of G vanish. Because all components of G vanishing is a very strict condition to
Mhm.
be met on neighborhoods, because
Mhm.
most metrics are not generated by Hessian. So that's why I was wondering, okay, well, what does it mean for a particular combination of indices? And then this carries forward the Poincaré's lemma applications and shows the Hessian potential. And other people have also noted when looking at this that because G is not tensorial, we can change a coordinate system at a given point
Yep.
to one in which the metric is Hessian at any given point on any given manifold. In the same way that Riemann normal coordinates choose a coordinate system to make all of the Christoffel symbols vanish, or the connection coefficients vanish.
But at
The
a
real
point or at a neighborhood you can do it?
at a point you can do it.
At a point, okay.
The real geometric restriction is whether or not we can do it for a neighborhood.
Mhm.
And on an open neighborhood, we can only do that if the metric is actually generated by a Hessian potential. And then this gets even more coordinate free. This is basically because earlier we had H sub sigma was one form. What this notation means is we're effectively assembling those together.
Yeah.
And H by itself with no index is just a homeomorphism from the tangent bundle to the cotangent bundle. And in equation 12, I just write that in component form. H applied to a vector field just gives the covector field of X. The only reason why I did all of the formalism in equation 11 is to show how the metric 1 forms appear in this lowering map, and to stress the importance of the metric in how we lower vector fields into covector fields.
So wait, I don't understand. So how is H different from just G?
H is different from just G because we have, because G by itself, obviously each component G mu nu is just a scalar function over the manifold. If we contract it with dx mu, we have a 1 form over the manifold. So H is basically the 1 form version of G. Each for each index for each metric each metric 1 form is just the 1 form version of the metric in a particular sector for a particular
so G
index.
is a function of 2 vectors, while H is a function of
just
a
one vector, right?
that gives you 1 form.
Sorry, it's
Well,
just like evaluating G half, right? Not plugging in
right.
2, just plugging in 1.
Yes, it's plugging in 1.
Right, that's what I'm saying.
Because if you apply H to a vector field, you get the covector field, and then you can apply that as a 1 form to a vector. This is basically, you could think of the square root of the metric.
Well, I'm just thinking that the metric takes 2 vectors and gives you a number, and this H gives me a vector. It takes a vector and gives me a covector.
Yes.
Right? That's it.
Yeah. It's just the partially applied metric.
Yeah.
And then you can evaluate the exterior derivative of this mapping by taking the exterior derivative of each individual component. And the reason you can do that is because the only part that will vary along the manifold is going to be the metric dependency. All of that is to say, okay, so now I get into how this connects to classical mechanics. Is because the Legendre map.
To bring it home. So I'll keep interacting because if I don't understand each point, I think it's going to be useless.
Sorry, I skipped.
So the point that you're making, I think, is that G alpha beta is going to be that exterior derivative of H, right?
Yes. Okay. So obviously here down in equation 13, what I have dH sub mu is you can substitute in for capital G, and this is going to appear. Yeah.
Okay.
And so we can say that dH without any indices vanishing on a region is precisely the condition under which the metric admits a Hessian coordinate description on that neighborhood. The reason why I say Hessian coordinate description is because normally the Hessian condition is defined in terms of covariant derivatives. But here we're using, normally the Hessian condition is using covariant derivatives. Here we're using coordinate derivatives. So this Hessian condition is going to depend on our coordinate system. And then I introduce a bit more notation that basically just changes how we think about the position dependence of, instead of considering this family of H mappings, we just consider the mapping at a point X. And that mapping at a point X is going to be a homeomorphism from the tangent space at X to the cotangent space at X, which is just going to take in a tangent vector at X and output the cotangent vector at X. This is exactly what Julius was saying of just it's the metric applied to one vector. Legendre map behaves in a similar way, where we have Legendre map is just a way of associating to each vector at a point X a cotangent vector. So we can relate this to classical mechanics by given a particle of mass m, charge q on a manifold. We note that the forward velocity u at a point x is just tangent vector at x. And if we let a sub x be the electromagnetic force potential at the point x, we define the fiber-wise Legendre map. So this is just going to take in, this depends on the point x, because it is fundamentally a map from the tangent fiber to the cotangent fiber at point x, and is defined as so in equation 16. which is it's a well-defined sum, even though we have the velocity in one part and not in the other, because both of those pieces will be elements of the cotangent fiber at point x. They'll both be covectors. And this is defined as script p because this combination is going to be our canonical momentum associated to the velocity. This is not particularly that important, but I just note, because we're operating from a Hamiltonian privilege point of view, this is not necessarily as important, but it can be noted that you can identify the Lagrangian that produces this after you transform it with the Legendre transform. But I don't necessarily prefer this approach because this treats the Lagrangian as primitive, and then you Legendre transform it. I'm looking at the Legendre transform more as the fundamental object that associates velocities to momenta. This is just the formal way of separating the velocity dependent part and the velocity independent part. Just splitting up our definition of momenta into the part that depends on the velocity and the part that doesn't. It's just separating into the kinetic part and the electromagnetic part. Now we can ask, if we fix a given velocity, so if we imagine just a vector field across the manifold that is completely constant, and we ask, what is the position dependence of this map? The way we evaluate that is we'll differentiate both Lx and alpha x with the exterior derivative, and we get equation 20. Once again, we get this dH object, and then F is used as the electromagnetic Faraday tensor. All of this connects back to classical mechanics. Sorry, this is not. Okay. The important part is the physical interpretation of this. The mathematics is just for the formalism and making sure everything is rigorous, but that's not actually what we're interested in, obviously. But MDH measures the failure of this morphism, which L sub x is just how we associate the kinetic part of the Legendre transform. The failure of that to have a scalar potential, and QF is the failure of the electromagnetic potential to have a scalar generator. Both of which have
scalar generator?
This has to do back with the Poincaré's lemma on so down in equation 6, when we noted that if a specific combination of G vanishes, that means that we can write some of the metric components in terms of the derivatives of a potential or a generator, depending on which word you want to use. If we think about all the possible ways metric components might be generated from these potentials, that's what DH, equation 16, encodes. And right, so that's what I mean.
I thought there was also an F, right?
Yeah.
So.
Right, because F would just be the curvature of the electromagnetic
right, so
form.
While QF measures the failure of the affine translation alpha x to admit a local generator, that would be the fact that the vector potential does not come from a scalar potential?
Yes. Yeah. Okay. So now we can ask if we, instead of just evaluating this at a point, I'm by evaluating, I mean evaluating MDH, evaluating this map. At a point, we can ask, okay, what if we evaluate it at every tangent vector along a curve? And when I say with minimal consideration of how the velocity changes, that basically means as we move along the curve, the tangent vector velocity is going to change, and that will obviously be encoded, but we don't want to do anything extra with it. The only incorporation of that change we want to have is the bare minimum of just how it changes. Really what we're interested in is the position dependence of the velocity to momentum map. expressed in local coordinates, that gives you equation 21, which is precisely what appears in the symplectic form when we use tangent space. All of that, so basically the punchline is that the symplectic form expressed over the tangent bundle instead of the cotangent bundle naturally incorporates the position-dependent variation in the Legendre maps. At every single point along an evolution, along a trajectory, this Legendre map is our rule for converting velocities into momenta. When we try to express the symplectic form in terms of the tangent space, we have to include position dependency of this map, because this map is not going to be the same at every single point in general. The metric dependent variation is encoded in DH, while the electromagnetic variation is encoded in QF.
But so F appears also when we don't go to velocities and we just go to kinetic momentum. So we use the lower indices form of the kinetic momentum.
Yes. In that case, our the mapping, we would still have this affine translation is the key point of we aren't necessarily mapping from the tangent space to the cotangent space, but we're shifting everything by this translation of, I write alpha, alpha is just defined QA.
Yeah, so I understand the math. It's the problem is
right.
that I'm still not. I don't feel that I have made any progress on the physics. Like it seems that the math is put, let's say, more better together, but
Right.
I still don't understand what's happening.
Yeah.
So
how at every point along a manifold, whether we think of the manifold, at every point in space,
yeah.
we have a rule of associating a velocity to position. However, that rule isn't going to be the same everywhere. And the reason it's not going to be the same everywhere is because the metric will vary, the electromagnetic potential will vary, and all of this. How this rule varies is encoded precisely in G. G encodes the kinetic part of the Legendre transform and how that varies.
Right. So in that sort of nebulous sense, yes. The thing to me is I need to understand what each component say, and then how is it related to a force? Like it seems to me that there has to be a geometric way to understand both the potentials, the P and the forces here. And I want to understand both for F that appears in a slightly different way, because F appears even if I just say I go from position to not conjugate, so from velocity, so conjugate momentum, not to velocity, but to, let's say, kinetic momentum. So I haven't moved to the tangent. I'm still in the cotangent bundle, but F already appears there. So that's picking up, let's say, a part of this change of map, coordinate, whatever you want to call it. And then we go to the other side. So in the diagonal, for example, it's a lot easier to understand for me why, when I just use position and kinetic momentum, the off-diagonal terms are still the identities, because I'm still in the cotangent bundle, and all that I did was a change between P and U that is just dependent on X. So the way that I count state, it basically didn't change. It's still the same. But then when I go to velocity, clearly the way that I count state is going to be different. And clearly there is a position dependent, because if I have potential forces, my velocity with relation to momentum is going to be different. And also, if I have if I'm not in flat space, then things are going to get screwed up. But I still don't understand exactly why and how is that related to forces. Does that make sense?
Yeah. I still have a few more things. I'll go through those, and then we can take it back.
Okay, I thought.
No, sorry. It's deceptive.
I saw summary,
it's deceptive.
and I thought you were done.
Yeah,
okay,
it's deceptive.
Sorry. Go ahead then.
Okay, because I also wanted to.
Okay, there you
yes,
go. Okay.
I also wanted to formalize because a few other people have said in the Discord, like, this is, the curl of the metric. I wanted to formalize how exactly this appears when we talk about curl
Okay,
and
good.
vorticity. And that's effectively just using, if we want to talk about the vorticity of a vector field at a point, we compute the line integral of the vector lowered vector field around that area. And then just doing the formal stuff of, okay, if you shrink down the neighborhood on what you're considering down to a point, the line integral will stay, but the area integral will just return the integrand, yada, yada, yada. Effectively, what we're doing is we're just evaluating the exterior derivative of the covector field at the point. So the vorticity of a vector field V at point X, I scrolled, is given in equation 26, which is just the exterior derivative after you lower it. But crucially, what I did was in equation 25, I split the lowered component of the vector field into the metric and contravariant components.
Okay, wait, because there are so many things that I need to unpack because
Yeah.
the notation just it jumbles everything in. So when you're doing the line integral of V flat, I don't even know how you say that. How you say
Yeah,
V
V flat.
Is it?
Yeah.
Okay. So you're effectively doing the line. So the one form that you're integrating, it's V contracted with G.
Yeah.
And then on the other side, you're going around so you're basically taking the V component along the path. That's what you're doing. That's what you're integrating over.
Yeah. And around that loop, infinitesimal loop around the point.
Okay. And you need, so I'm trying to understand. So this is something that you can't do if you do not have a metric tensor. Because if you don't have a metric tensor, the only thing that you can integrate are one forms.
Correct. And if you start with the vector field, you have no way of identifying a unique one form.
Okay, and then you say Stokes' theorem, then you just do that, and then you got that. Okay.
Yeah. And yeah, equation 25, I used product rule to split up the metric and the contravariant components while maintaining this anti-symmetry. Because the exterior derivative appears in Stokes' theorem, it's going to be anti-symmetric over these indices.
Yeah.
And then I put that in equation 26. Instead of writing out the anti-symmetric brackets, you have the wedge product that appears there, because fundamentally what you're going to get from this is a two form, and the wedge product will enforce anti-symmetry. On the next slide, I express that in components. Each component of the vorticity, which is equation 27, which with a little bit of notation there. But what equation 27 is it is the vorticity of the vector field V at point X in the mu nu plane. Now, this will obviously be coordinate dependent, because when we talk about different coordinates, what we mean by the mu nu plane will change. But in a given coordinate system, this is well defined. And the reason why this split is helpful is because G, capital G, is encoding the anti-symmetric partial derivatives of the metric, while partial star is evaluating the anti-symmetric partial derivatives of the contravariant components of the vector field. Effectively, what's happening is capital G is encoding how the metric is curling in the mu nu plane, and the other term is encoding how the vector field itself is curling in the mu nu plane. And we need both when we talk about the vorticity of the vector field, because of the fact that to talk about the line integral in the first place from the previous slide, we have to lower the vector field with the metric first. In that way, capital G encodes how the sigmoth sector of the metric curls in the mu nu plane, which directly connects to why G appears as an obstruction to the metric being generated by a potential is this this notion of the metric curling.
Yeah, I just need to understand that at some point geometrically what it means, because again, I understand it mathematically, but yeah, what is it that it's curling about the metric? Because
effectively, when you want to talk about how a vector field curves, or not how a vector field curves, how the circulation and the vorticity of a vector field, part of what you're going to get is the actual vector field circulating. But part of what you're get is going to be a remnant of the fact that the metric itself might be changing in a circular manner, and that is encoded in G.
Yeah, so as I said, I can understand it mathematically. What I would need to understand is, okay, the metric defines, lengths with rods, and therefore you're going to make a path, and this is the rods that you're taking. Look at this. When you do a full loop, your rod does not come in the same place, and that means I would need something like that, right?
Yes, that's what because back to the metric one forms and the exterior derivative of the metric one forms. Where do I have that? Equation 2. The failure of H sub sigma to be closed is encoded in G because it's the exterior derivative of that. The failure of a one form to be closed corresponds to the anhalonomy, which, like you said,
look, you're still throwing math at me.
Okay, yeah. I was just going to bring this back.
math.
I was just going to bring this back of exactly what you were talking about with if you transport rods or rulers around a loop, the ruler may change length as you get back. And that is encoded in the failure of these metric one forms to be closed, which is G.
Right. So what I need to understand, so I suspect that imagine it like this. I have a rod, I make it go through a square, and then there's going to be a change in the rod. Right?
Yes.
Or in the thing that evaluates the rod, because these are one form. So I suspect that these are the things that I give the distance, I give it the rod and it gives me the distance along some trajectory, but that's fine. So the point should be, I have a rod that starts in a particular direction, I make it move through two directions and I'm gonna get something, right? And so I suspect that the mu and the nu are the two directions in which I'm making the loop.
Yes.
Right? Because that's the plane.
Correct. So if you can think about your ruler as being a vector that we keep constant around the loop. We want to keep the same direction and everything, and we're just curious about moving this vector around. In that case, the second term on the right-hand side of equation 27 will be 0 because of the partial derivatives. It will vanish.
There you go. Okay.
So as you move around, what you're going to get is the vorticity in the mu nu plane directly encodes the failure of this vector to come back to exactly where it started. And if the vector itself is constant, in the case of moving a ruler around a loop, the only non-zero term you're going to get is G mu nu sigma contracted.
So, okay, good. So mu and nu, we agree, are the direction in which I make my little closed loop.
Correct.
Then sigma is going to be the direction in which I oriented my ruler.
Correct. Okay.
Then I come back and G mu nu tells me the difference in that direction.
How that has changed. And I'm not
if it's positive, it's going to increase, and if it's negative, it's going to decrease, or it's a multiplicative factor. If it's positive, it's get stretched, and also if it's greater than 1, it gets stretched, or if it's less than 1, it gets shrink. Like what is the coefficient telling me?
Because this came from vorticity and Stokes's theorem, the coefficient would tell you how much this vector is rotated in the positive orientation, so counterclockwise, when you get back to the starting point.
How much is rotated?
Yes. I do not believe you would have any intrinsic stretching.
Okay,
There
so
is
this
only
is exactly
rotation
the
of
type of thing that I want to be
yes.
clear, Logan. Just
Right.
just in general, right? When I have this question, what does this thing mean?
Yeah.
I want to understand it this at level. Okay, so I have two directions in which I make the loop. I
Yep.
take my rod, which is in a separate direction. I make it go around. And you say it rotates, but now to say that I have a rotation, you need to give me a plane. So is it a rotation along the same
Mu-nu
plane?
plane. Yes, it will necessarily be in the same plane of rotation as you moved it around, because of how G was defined with a two form in the mu-nu plane, which this is still what I'm actively thinking about, because I suspect part of why this rotation will necessarily be in the mu-nu plane will have to do with something with either metric compatibility or something, but that also doesn't make entirely sense because we haven't necessarily introduced a connection here. We aren't using covariant derivatives, we're using the partial derivative.
Okay.
But I believe just from how G was defined in terms of the exterior derivative of the metric in the mu-nu plane, that this rotation will necessarily be constrained to the mu-nu plane without any stretching, unless the vector itself changes. Then the vorticity can be whatever which way because of the second term. But if you keep the vector constant and move it around the plane, the only possibility of it not returning to where it started will be a rigid rotation in the mu-nu plane that is encoded by G mu-nu, contracted over the sigma index, which is the same plane that you transported it in.
As a test, if the direction of sigma is perpendicular to both mu and nu, I would expect G to be zero then. Because it cannot rotate.
Right. Yeah, that would be a good test. Yeah.
Maybe a small comment is whether this applies to all the planes, because how many planes can you define in the whole space? So one plane is not enough to set the metric to to a trivial one. You need to apply this for what, 3, 4 planes, and then conclude this. Otherwise, in one plane you only have this conclusion that is flat. In other planes you still have an arbitrary dependence.
Right. Because you can consider transporting it in all possible planes attached to a point and sort of get a complete picture of how this transport would work. And that would, the number of planes that you have attached to a point will depend on the dimensionality of the space. But yeah, I'm not entirely sure on the perpendicular point, which is something that I'll have to think about more.
Yeah, so look, this is the type of thing that you just, or anybody who's watching, these are the type of things that I'm interested in. So I have the math, right? Good, and I understand it's, it's, I'm pushing symbols, so I understand it as pushing symbols, but I understand what's going on. And then I want a tight physical interpretation in terms of stupid, simple operations. And then they give me some insight, and then of course I want to see that insight is back in the math, because otherwise I have the completely the wrong intuition. So
this intuition of moving the vector around and not coming back to where it started was exactly what I was picturing when I was saying that the metric rotates. I just didn't make that as explicit, which is what I should have done instead of just relying on the math.
Yeah, but that's fine. I'm here exactly to sort of, as long as you accept that I'm going to stay there and keep going back to it, absolutely fine. I mean, this for me is a lot of fun, so good. Okay, so we have a very good candidate in what then G is with respect to, rods and movement, because you're basically saying with the vorticity, the important thing is that if the rod remains the same, then that second part is zero. Correct. And therefore, the only thing that I'm doing is this transport around, which the thing that it's interesting to me, and that's another thing that I want to understand, is that when we do the curvature, right, the Riemannian 4 tensor, We are doing a similar thing. So how is it different? Because I feel that this is going to pick up some part of that idea, but this is coordinate dependent, while the R is coordinate independent. And I think there has to be because my secret goal is to hope that there is some type of like simple in quote operation that we can do to G to get R. Right, because we are kind of doing this thing. We're looping around and doing something like that. And yeah, so anyway, go ahead.
Yeah, that pretty much finishes off what I had. I just attached on 2 sides on frame transport today, because yesterday we were talking in the Discord server about frame transport. But those slides were mostly for me because they are just a wall of text that I don't think helps anyone. So I will save this for when we talk about what some other people are thinking about. So yeah, that finishes as far as my explicit presentation goes.
Yeah, so yeah, first, congrats for writing up all this maths. I would not have guts to even attempt to do this.
It was a lot of LaTeX practice, I will say that. Yeah.
Yeah, that's why I'm just usually attaching these handwritten slides instead of LaTeX, because I just don't have enough patience to type the formulas, which might
That's
not
fair.
might be only distracting in the end. But going back to the topic. I would suggest maybe like giving a like different view, but for that maybe could anyone share the part from the book where we have let's say this definition of big G and this let's say Newton's second law in terms of the Christoffel symbol and the Faraday tensor.
Yes, I'll do it. So you want this part?
Maybe lower, like at the end of the page.
Yeah.
Yes,
Where is
for
it?
example, yes, this one, for
Yeah.
example. So this is basically Newton's second law in disguise, if you read it correctly. And now, so we don't have too much time, so I want to be, just very quick. So what we see on the right side, we have the force, which from the electromagnetic part, it depends linearly on the velocity, and on this Christoffel part, it depends quadratically. And now, what we know about, so this is now a discussion, let's say, from physics. So let's say this reverse physics approach, because we have reverse physics and physical mathematics, and I want to, take them separately because, otherwise we get into confusion. So what we know from electromagnetic forces in general relativity, what we know is that they only introduce they act perpendicular to the velocity, meaning that the vector, the energy is preserved. The only thing is that the vector is rotating, and that's what we see in the symplectic form. That again is the same part which is responsible for the rotation of the vector. Now, of course, we should also pay a certain attention to the electromagnetic force as a physical theory, and this electromagnetic force that we derived from the vector potential, because the vector potential was, let's say, this constant of integration that we introduced. A priori, this is not necessarily related to any field theory. It can be even an offset by let's say, or offset of momentum by some constant, basically different point of reference point. So in this case, let's say we use the same symbol for two different things, but regardless, what we see in the symplectic form and what we see from physics is that the electromagnetic force only introduces the rotation. And that got me into thinking what information symplectic form extracts. And here, what would be maybe also helpful is if we introduced a force generated by a gradient of a scalar. So let's say we had some potential that is not a vector potential, not coming from a metric, just some scalar potential, which we usually exclude, or we say that we can absorb it into parameterization. It's fine. What we would see is that scalar potential would not appear in the symplectic form. And why? Because scalar potential affects the energy directly. There is no freedom to rotate a vector. It only, we only see it explicitly in the Hamilton's equations of motion. In the symplectic form, what we usually see are the effects which do not change the energy. Is that it's any possible operations of kinematical variables which preserve the energy or the length or whatever, but they still allow some freedom. So the motion is not completely frozen, but it is not, there is no friction, there is no like energy exchange. So what I thought is that that's G, big G, should also correspond to something like rotation, meaning that we are not changing lengths, we're not changing angles, which are also coming from the inner product. So it's the same thing. We can use the metric, to define the length and to define inner products. So this operation should not do that. It means that what again remains is rotation of the frame.
Okay.
And but this one, but here there should be a distinction from rotation versus carrying a vector around a closed loop, because these are different operations. So basically, so now if the interpretation from the physics part is that symplectic form is basically is kinematics, it's not dynamics. We do not see why the force is generated, why the energy is increased or reduced. It's only, it might be relabeling of indices, it can be mixing of the reference frame, but it cannot be, anything that, accelerates or decelerates the system. So now, what happens if we now go back to the Newton's second law? We have that this Faraday tensor is already antisymmetric. So if we tried to multiply by 4 velocity, it disappears. So it means that the length is not affected. Fine. However, when we look at the Christoffel symbol, with respect to the first two indices, we have anything. It's not symmetric, it's not antisymmetric, anything is allowed. So now what is usually very useful in algebra is this decomposition, which is called trace-free, symmetric, and antisymmetric. And symmetric part encompasses the trace and trace-free, while antisymmetric is its own part. So now symmetric part usually describes this isotropic behavior, something that does not depend on the angle. So this is like expansion or contraction of the whole volume. And this part actually, this is the part that some people might remember when they calculate the trace of Christoffel symbol, which gives this derivative of logarithm of square root of determinant of metric. There are these things sometimes appearing. And what this does, this generates basically, when we contract with 4 velocity, this will generate a part which is proportional to 4 velocity. And anyone who knows anything about, let's say, conformal, let's say conformal rescaling, they will already tell that, okay, you can kill this part by changing parametrization. So this is the part, this pure isotropic part is something that you can kill just by changing parametrization along your trajectory. So you change the time, you kill this part for any coordinate system. Then there is the remaining part, which is also of the symmetric part. This is called shear, or this. Basically it's like the part that deforms circle into an ellipse. So this is really the part that comes for, this is a different part, which let's not discuss now for much, but it also belongs to the symmetric part. And so what we can agree that neither of these two appear in the symplectic form. So these are irrelevant. What is remaining is only the antisymmetric part. And so it is neither expansion nor the shear. So the remaining part is usually called vorticity, and we saw the word here used very often, which is vorticity. So now, how to understand that? So I was thinking about it for some time, and then yesterday I think we had some discussions in the Discord server, and we agreed, we agreed on the notes that Logan made yesterday, but didn't finish maybe for this talk. Basically, we reached the same conclusion. So to extract, if we want a physical operation to extract this antisymmetric part, what we need to do is we need to define an orthonormal frame. So basically 4 vectors, unit length, all of them are 90 degrees with each other. And we ask what happens when you take the derivative along the curve. Since these 4 vectors span the whole space and they're a unit length, the net operation has to be some rotation matrix. It has to preserve their lengths. And from here, now, of course, since we're using ordinary derivatives, there is always this additional part that comes from the derivative of the metric, or this lead drag of the metric. If we used covariant derivative, then this rotation matrix would be antisymmetric. And this would, this rotation matrix can be expressed in terms of bivector spanned by any 2 legs of this frame, contracted with the Christoffel symbol, and due to symmetries, it extracts exactly the antisymmetric part of the Christoffel symbol. So you can interpret this that the net rotate, that each vector of the orthonormal frame, as we propagate along the trajectory, it is rotated, and basically is rewritten with in terms of the rest of the vectors, and this rotation matrix is covered by the antisymmetric part of Christoffel. So basically, if we want to measure this part, we need to measure how the frame is rotating. So now to get
Julius,
back,
we would need. I completely get lost, so I would need some kind of like slow with the equations on. Like I'm not able to follow.
Okay. So then, let's say the net conclusion is that the antisymmetric part, what it does is just, let's say if we start with some initial coordinate system.
I need the equation. Otherwise, I completely get lost. So the thing that is interesting, though, that I didn't realize of something that you said and relates to the others. So if we're looking for velocity, the norm of for velocity is always constant. And so the fact that the only thing that the evolution can do is just rotate the for velocity, that's basically an obvious, it has to be like that. It can't do anything else. So the fact that the electromagnetic force field does that is in that. But now it also tells us that the inertial part also have to do that. And so what we are interested in terms of the forces then, it's going to be exactly the vorticity where the part of the vector remains the same, like the vector remains of the same length, because we're actually looking how those things rotate. So I even more like integrating the parts that I've understood of what you were saying and what Logan was showing. I even see even more of a physical reason why you're interested in this curl of the metric tensor, because it exactly tells you how the vector is going to rotate, therefore how the velocity is going to change by the action of the fact that you have different coordinate systems. So that now makes a lot more sense to me.
Yeah. Now, of course, even though the velocity is the magnitude of velocity is conserved, it does not say that the Christoffel is already antisymmetric, because we have to interpret it with respect to the notion that we have in flat space, in Cartesian coordinates. because if we took this as flat space but different coordinates, that's why we have additional terms. That's why Christoffel is not the antisymmetric part but the whole term. If it was pure rotation, then yes, we only have antisymmetric part, but we have the full Christoffel because this how to say, we still have we have to differentiate in which coordinate system we measure the length, because if we measure in Cartesian, then the coefficients of the metric are -1, 1 on 1. If we change the basis, now they are position dependent, so it's not -1, 1 on 1. It is something else, and these differences then appear as the symmetric part of the Christoffel. So that's why we have full Christoffel. But yes, it is. The conclusion is that the antisymmetric part should tell us about the rotation of the frame, but it is the frame tracked by this single point on the trajectory. It is not. It is not the vector taken along a loop. That is a different thing which should
that we agree. So that the two things are related, and it needs to be clear how they're related. But there is still the idea that on one side we're taking something and making it a loop, and then the other thing is that we are transporting the same thing and see how it's that thing itself is rotating. Yeah. Those are two different things that are related, and we need to understand how they're related.
Yes.
I don't know if Isaac wanted to say something, since he has been quiet, or it's fine.
I mean, that's the point, that if Isaac could share the slide that he put on Discord last day, then this would be exactly what I wanted to say. So I don't know why it was not included. Because that was exactly the equation.
You asked me to share from the book, so I shared from the book.
Yes, but no, I mean, Logan had something. Sorry, I forgot whom I was discussing with, but there was full page of calculations, and it was exactly my formula. So yes, this one. So basically, what I said is that here, if we need to take psi, and so now there's this psi AB mu. Mu is the coordinate index, which is what we used. AB are so-called tetrad indices. They are labeling these orthonormal legs. So we have 4 vectors spanning the space. Hence, we have 0, 1, 2, 3 going into AB. And if we contracted psi mu with 4 velocity, the remaining part is the rotation matrix. And I think there was one outcome that we discussed in text, but it does not appear in formulas. But yes, it's due to rotation of the frame.
Okay, I couldn't I didn't have enough time to digest the math.
Yeah. Okay, so then I will. So I guess for now, also from my side, I don't think I can contribute more to this. I think my message to take away from here is that this part is that extra part is basically rotation of orthonormal frame. That's we started initially with some labeling. We had X, Y, Z, T, and then because of behavior of the metric, the labeling is this frame is changing. Because we always have vector contracted with a matrix.
Julius, I have to go slowly because otherwise I don't understand anything. Okay, so we start with EA and EB. Those are two coordinate bases, right? They're the basis vectors. That's the idea?
No, EA are the orthonormal vectors.
EA and EB are two orthonormal vectors.
Yes.
Okay.
They have representation in coordinate basis, but at this point, these are just vectors which are pointing in 4 different directions.
Yeah. Okay. So we have E and A. Okay. So then you say, I move things and they will remain orthogonal, And so I have a relationship between their changes and the changes of G. And then I say, well, I want to define G on one of the vectors and on the change of the second vector with respect to that direction. And so I define this CAB mu, which is just going to be 1/2 minus 1/2 the derivative of G, okay, on how do I know that it's the second one? It doesn't matter it's the second one because it's going to be symmetric, so who cares? And then you make the anti-symmetric, okay, of course, and that's going to be now the G that we have. So you have the anti-symmetric part is going to be that plus 1/2 of the derivative, and then you get okay, or you are just making the change of one or the other, which we can verify is equal to 0. And then you find that you have an omega AB mu, which is that thing that we were doing. Oh, we are using then the covariant derivative. Okay, yeah, I can't really understand. Okay, so E, yeah, I don't know if we're gonna have time for me to digest
Yeah,
all of this.
so I think
Wait,
this
Logan,
is
you're muted.
sorry. So
Logan.
this last line, I think we don't have to pay attention. This spin connection is what appears if you studied that this tetrad field or frame field theory, rigorously. This is not necessary in this case. I think
Agreed.
what is important is that at some point you can express this psi as a contraction of this bivector formed of two normal vectors contracted with Christoffel.
Mhm.
And what remains
that's,
is yeah.
And that's what you were mentioning in the conversation as it progressed that I didn't have time to include in that write-up was that explicit rotation connection. But I agree with the conclusions you got to, yeah.
Okay, maybe we'll discuss it some other time when we have a better narrative so that I can follow better, because like that I didn't follow that much.
Right.
Anything else you guys want to discuss? Or we close it here? Are there questions from the chat? There were some viewers on YouTube as well, but I didn't see any activity on the chat, which I am monitoring.
I mean, yeah. There's obviously more to discuss, but I think all of that can be saved until a later date, done in the Discord server. All of that.
Right. The point is that if we have something that can be discussed in 10 minutes and not in another hour.
Right. Yeah.
Okay, no, that was very good. Like, I think, this is definitely progress. And as I said, I'm more interested in this like silly operational thing of what is it that we're actually doing. And yeah, so we can proceed. I don't know if I have any topic for next live. I think I'm traveling next week. Let me check. Yes, so next week I'll be traveling, so I doubt that I'm gonna be able to be online. I'll double check, but tentatively we can. And then I'm gonna be traveling in August, but I'm gonna be here August 1st at least. So yeah, so if there are topics that people want to discuss on the next year, like with the conferences, I found a couple of people that I want to invite to chat, so that'd be good. And Logan, Kayla relationship, and Essian, yes, all of that.
Yeah,
And
I was just briefly looking through the Kaler stuff that Nicholas put onto there, and it it is directly related to whether or not the metric is Hessian, which comes from the whether or not the metric is itself curling. So there
Right.
is a direct relationship there. Yeah.
And then there is the Kähler thing is also interesting because so it's something that I will want to recover in the space of ensembles because there is a natural metric that comes out of the of informational geometry that it's comes from the entropy, which is the Hessian of the entropy. So you take the Hessian of the entropy, that gives you a metric on the space of ensembles, both in classical mechanics and quantum mechanics. And in quantum mechanics, you also have a symplectic form on the space of pure states. What I need is that symplectic form, which is not going to be a symplectic form. I need a Poisson structure extended in the space of ensembles, and it should be that the space of ensembles is foliated by the entropy. So every every fiber of the entropy should be in some sense asymplectic, well, not manifold because we're going to be infinite dimensional, but you know, it's going to have some type of symplectic structure, and it's going to have some type of the metric that comes from the entropy itself, and so there has to be a link between those two, and whether it's exactly the type of link that you would have in a Kähler manifold, I don't know. And again, it's not going to be a manifold anyway, because we need to be able to do it in infinite dimensional, even in classical mechanics. Because if we look at the space of probability distribution, that's going to be infinite dimensional. But again, we're going to have this type of thing. So it's stuff that I want to generalize, but I do not know whether the Kähler is too much of a ad hoc case for, let's say, finite dimensional things, that then if you go to infinite dimension, it's going to become much more complicated. But it's in the realm of things that I want to understand. So okay, so
yeah.
we can schedule for the next one. We can already say that we're talking about this.
Yeah, and because especially if you're gone next week and if it's in 2 weeks, that's enough time to develop things further and connect things to each other and everything. Yeah.
Julius, you wanted to say something? I think I interrupted you.
Maybe not about the next topic, but more just the comment that's even if the Kähler manifold can be useful for quantum mechanics and what you mentioned, in this particular case, this is actually quite constrains the possible geometries, because we know that this is standard exercise that we need 20 independent components which are then covered by Riemann tensor, and if we have the scalar, then it's just one component. We have still 19 components to describe the rest. So if there is a need for Kähler manifold, it should not come probably from here.
Okay, so I think we're done for today. And thank you, everybody. Thank you, Logan, for putting everything together. Thank you for the nice discussion. And we'll see, if not next week, in 2 weeks. Bye.
Bye.
There we go.